So let's first consider different classes of linear differential equations. First order differential equations. A number of processes and their dynamic behavior can be defined using the following generic first order differential equation. Tau times dy over dt plus yt equal to k times ut. As I mentioned earlier, as long as a process is defined, the dynamic behavior of a process is defined by first order equation, we will always be able to express it in this form shown here, where tau is referred to as time constant for reasons we're going to learn later. K is referred to as the gain of the process. And in the rest of this course, we are going to be using y to denote outputs or control variables and u to denote inputs or manipulated variables. Let's take a look at a few examples of processes whose dynamics are defined by a first-order differential equation of the form shown here. Consider a simple process with a tank, an inlet flow rate and an outlet flow rate, where the outlet flow rate is a function of the height in the tank. This process is defined by the model shown here. H is the corresponding output, Qi is the corresponding input. Now the model as written initially is not in the standard form. However, if you divide that equation by KQ, you can rewrite the differential equation in the common generic form. Now in this particular case, the gain K is 1 over KQ, the time constant tau is A over KQ. The second example here is that of a similar tank, but instead of being interested in mass balance, we are here interested in energy balance. By writing an energy balance equation on this process, we can show that the corresponding energy balance equation can be expressed in the standard first order differential form, and the gain of this process is equal to 1. The time constant is V over Q. The gain in the second process must be equal to 1 because the amount of change in the temperature in the inlet must eventually be equal to the change in the outlet. In other words, the change in input must be equal to change in output, and therefore the gain is 1. Now, we can derive a transfer function for this differential equation, a generic transfer function for a first order process. We go through the standard steps. We write the dynamic model, write down an equation for the steady state model, subtract the steady state model from the dynamic model to express the differential equation in the deviation form, and then apply Laplace transforms to derive a transfer function between the output y and the input u. The transfer function that you see here is very important. This is a transfer function that you will come across quite often, and it's called the transfer function of a first order process. It's given by k over tau s plus 1, where k is the gain of the process and tau is the time constant of the process. Remember that when you write a transfer function on the left-hand side, you always have the output over the input. You never write input over the output. K is the gain of the process and tau is the time constant of the process. Also remember that the transfer function is always defined between deviation variables and it's never defined between the raw variables. So the objective of this section is to study the dynamic behavior of processes defined by first order transfer functions. How do they respond to a step change in the input? How do they respond to a step change, to an impulse change in the input, or a ramp change, or a sinusoidal change in the input? So those are the questions we want to answer in the rest of this lecture. Let's first consider a step input. In the deviation form, the step input us prime is going to be equal to 0 for negative times and is going to be equal to a constant of magnitude m for all positive times. The same input in its raw form is going to take a different value. In its raw form, it's going to be equal to u bar for negative times and is going to be equal to u bar plus m for all positive times. I want you to clearly understand the difference between the input in its raw form and the input in its deviation form. We can of course plot this on a graph. The input initially, the raw value is u bar, the final raw value is u bar plus m. On the other hand, the initial value in deviation from is 0 and the final value in deviation from is equal to m. There are a few examples that one can consider where the inputs are similar to step inputs. For instance, turning a light switch is an example where the input, the current, can be changed in a fashion that is similar to a step change. Opening a valve is another example, or heating water on a stove. When you change the knob on the stove abruptly from one position to a new position, that is equivalent to changing the heat input to the process in a step fashion. Now let's try to understand how a first order transfer function responds to step changes in its input. And one way to study the effect of a step change in the input on a first order transfer function is to go back to the transfer function, replace the Laplace transform of the input by the Laplace transform of a step change. In this case, the Laplace transform of the step change is m over s. And therefore, y is equal to the first order transfer function times input. Now we can replace for the input in Laplace domain, it's m over s. We can obtain the value of y, the response, in time domain by taking the inverse Laplace of y prime s. Using partial fractions, we can split y prime s into two smaller fractions and then find their respective Laplace inverses. And that results in a response of the output y prime t, which is equal to k times m times a step response st minus an exponential function. And that response is valid for all values of time greater than or equal to 0. Let's substitute t equal to tau. That gives us an output that is equal to 0.632 times km. In other words, when time is equal to tau, the output is going to be equal to 63.2% of k times m. Let's represent the transfer function using a block diagram. K over tau s, we're going to replace, from now on, we're going to replace the process in the block diagram with the transfer function. On the left-hand side, we have the step change in the input that results in a step response of the first order transfer function. And on the right-hand side, I'm going to show you the step response of this transfer function. The step change in the input is often referred to as a bump test in industrial settings. So the response starts at its initial value y bar and reaches a new steady state value that is equal to y bar plus k times m. And the change in the output is equal to k times m. It is important to notice that for every change, every m units of change in the input, the output is going to change by k times m units. Also, note that at t equal to tau, the output is equal to y bar plus 0.632 times km. In other words, the output reaches 63.2% of its final value. Now, if the time constant is smaller, as in tau 1, the response is going to be faster, and if the time constant is larger, as in tau 2, the response is going to be slower. In other words, time constant is a measure of how fast or how slow a process responds to changes in inputs. In real industrial settings, often it's very difficult to derive a differential equation from first principles using mass and energy balance equations. On the other hand, we often know from the dynamics of the process that the process is perhaps represented by a first-order differential equation. And if a process is represented by a first-order differential equation, its transfer function is going to be k over tau s plus 1. But because we are unable to derive a differential equation from physical principles, we will not know the gain k or the time constant tau. In those situations, we can perform a bump test on the process, obtain the step response, and from the step response, we can back calculate the gain of the process k and the time constant of the process tau. This process of estimating the gain and the time constant is what is called identification or parameter estimation. The first order transfer function magnifies or suppresses the input change by k units, And the time constant is the time taken to reach 63.2% of the final value of output. It represents the speed of response. In a first order plus dead time process, we're going to use the short form FOPTD to denote first order plus dead time processes. The transfer function is given by k over tau s plus 1 multiplied by an exponential factor e power minus tau ds, where tau d is the time delay. On the left-hand side, you have the ratio between the output Laplace transform and the input Laplace transform. You must always write the output Laplace transform in the numerator and the input Laplace transform in the denominator. We've learned that a first-order transfer function is subjected to a step input with no delay. The input and the output change simultaneously at the same time. On the other hand, when there is a delay present in the first-order transfer function because of the delay in the process, if your input changes at time 0, the output is not going to change at the same time. Instead, it is going to change at a later time. In this case, because the time delay is tau d, the output will start changing at time tau d. We can also notice that even though there is a time delay, the only difference in the response from the response of a non-time delay first-order transfer function is that the response is going to be shifted by tau d units from the origin. The overall change in the response is going to remain k times m, where k is the gain of the process and m is the magnitude of the step input. And the other difference in this response is that the output is going to reach 63.2% of its final value at time tau d plus tau. If there is no time delay, or if the time delay is 0, it reaches 63.2% of its final value at time tau. Now let's look at the ramp response of a first-order transfer function with time delay or without time delay. The ramp input is one which increases linearly with time. Let's assume that it is 0 for negative times and it's equal to a times t for positive times. A typical ramp input is shown here in the plot. And the Laplace transform of a ramp input is given by a over s square. While ramp inputs are not very common, they're also not uncommon. For instance, ambient temperature, the way in which it increases from night to day and again drops from day to night, is something we can approximate using a ramp function. Acceleration or deceleration of a vehicle can also be approximated using a ramp function, and often in the process industry, step changes are not implemented as such, because if you make an abrupt step change in the valve position or in other manipulated variables, that change can often result in excessive wear and tear on the final control elements. In other words, abrupt changes such as step inputs, when made often, will lead to excessive wear and tear on the final control elements. So instead of making step changes, we often approximate them using a combination of a step change and a ramp. That's another instance where a ramp function could potentially be used, and therefore it's important to understand how a first-order transfer function responds to a ramp input. The ramp input is given by a product of a constant a and the time t. The corresponding Laplace transform is a over s square, and therefore we can substitute this in the first-order transfer function. I've chosen here first-order transfer function with no time delay. We go through the standard procedure of finding the partial fractions and then finding the inverse Laplace transform. It turns out that the ramp response of a first-order transfer function is given by this exponential term and a linear term in time. This is the linear term in time, and this is the exponential term in time. For large values of t, obviously, you can take the limit of y prime t as t goes to infinity, and you will notice that for large values of t, y of t is a linear function of time. In other words, Eventually, as t goes to infinity, the output will also approach another ramp with a different slope. And the slope of that ramp is going to be k times a. I have here a plot of the response of a first order transfer function to a ramp input. What you see here is the ramp input, and this curve over here is the output of a first order transfer function to a ramp input. There is going to be an initial transient region followed by a ramp. Now let's consider how first order systems respond to impulse inputs. Impulse inputs are represented by the Dirac delta function, as you all know, and the Laplace transform of a Dirac delta function is simply 1. And therefore, the output of a first order transfer function to an impulse input can easily be obtained by multiplying the transfer function with the input Laplace transform. You can go through very straightforward algebra involving inverse Laplace transforms and arrive at this function, which is the impulse response. Of course, this can be plotted like all other responses, and it turns out that in an impulse response, there is an initial jump in the response followed by an exponential decay. And the size or the magnitude of that initial jump is k over tau. Now let's look at the response of a first order system to a sinusoidal input. This is interesting because unlike other responses, the response to a sinusoidal input also turns out to be a sinusoidal response. Sinusoidal function in time domain can be defined as follows. It's equal to 0 for times less than 0 and is equal to a times sine omega t for times greater than or equal to 0. And here is a plot of a simple sinusoidal curve that goes through the origin. The amplitude is the height of this sinusoidal curve, and the width here is a measure of the time period of the sinusoidal curve, and it depends, of course, on the frequency of the sinusoid. The Laplace transform of this function is aw over a square plus omega square. A couple of examples of sinusoidal curves: alternating current, that is something that you must all know. Often you will notice that various process variables oscillate at the same frequency. This is not uncommon. Here I have data from a refinery in Singapore. As you can see in the data, on the left hand side you see 19 different variables in this refinery, and there is a persistent pattern of oscillations in these variables. It turns out that these oscillations actually originated in a certain variable and propagated through the entire refinery. So seeing these oscillations, which are very similar to sinusoidal input, is something that is not uncommon. So let's study sinusoidal response of a first order process. Now we go back to the definition of Laplace transforms and the definition of the sinusoidal function, which is a times sine omega t. The output is calculated as usual by multiplying the transfer function with the Laplace transform of the sinusoidal wave and then using partial fraction expansion. The Laplace inverse turns out to be this expression here. I don't want to go through the math, but the math behind this is quite straightforward. You should be able to find it in the textbook. Now what you will see or notice is that this response has two terms, two important modes or terms. This is an exponential term and there is a trigonometric term. The trigonometric term is responsible for oscillations in the response. And as you will notice from here, that the exponential term eventually is going to go to 0 because it's stable. Using the simple trigonometric identity sine a plus b equal to sine a cos b and cos a sine b, you can simplify this response into two terms, one that depends only on the exponential term and the other that depends on the sinusoidal function. Now it's very easy to see that the exponential term goes to 0 as t goes to infinity, and therefore eventually the output of a first order system to a sinusoidal input is also going to be a sinusoid. But the important thing to remember here is that this output sinusoid is going to have a different lag. It's called phase lag. And the phase lag phi is given by negative tan inverse of omega tau. And the amplitude of the response is not going to be A. A is the amplitude of the input, but the amplitude of the output is going to be K times A over square root of omega square tau square plus 1. The input and the output, however, will have the same frequency, and the exponential term vanishes as t goes to infinity. So in summary, the response of a sinusoidal input is also going to be a sinusoid of the same frequency, but with a different amplitude and a different phase. So consider a simple tank with an inlet flow rate Qi, exit flow rate Q0 that's proportional to the height in the tank. The corresponding transfer function between the height in the tank and the inlet flow rate is 1 over As plus Kq, where Kq is the coefficient that relates the height to the exit flow rate. The goal of this exercise is to plot the change in height as a function of time when a volume of 5 meter cubes of water is instantaneously dumped in the tank. Now this action of dumping water into tank is equivalent to an impulse input because it results in a momentary increase in the input. And therefore, we can use the expression Qit equal to 5 times delta t, where delta t is the impulse. The magnitude of this impulse is 5 units. We can multiply the Laplace transform of Q with the transfer function and then take inverse Laplace transform to obtain the response in height as an exponential function. The interesting property of this exponential function is that when t equal to 0, you will notice a sudden abrupt increase in the height. The magnitude of that abrupt increase is going to be 5 over a. That increase is going to be followed by a rapid exponential decrease in height. In other words, when you quickly dump water into a tank such as this one, you will notice a sudden abrupt increase in the height. But as time goes, this level will eventually go back to its previous steady state because there is no more additional water entering the tank, and whatever water you've dumped into the tank momentarily will eventually leave the tank and the height will go back to its initial steady state. So that's the typical impulse response that you would see from a first order system. So let's consider processes defined by second order differential equations. It turns out that just like processes that are defined by first order differential equations, there are a variety of processes that are defined by second order differential equations of the following form. Tau square d square y over dt square plus 2 zeta tau times dy over dt plus y equal to k times ut, where tau is the time constant and it serves the same purpose as the tau in the first order transfer functions. It determines how fast a second order system responds to inputs. Zeta is a new constant that appears only in second order systems, and it is what is called a damping coefficient. K is the gain of the process, and it has the same meaning as in the first order transfer functions. Now let's consider two tanks in series. I want to prove to you that when you keep two tanks in series, the resulting differential equation that relates H2, height in tank 2, to the inlet flow rate into tank 1 is going to be a second order differential equation. Now this must be something that is somewhat obvious to you because we already know that each of these tanks are first order tanks. Their dynamics are defined by first order differential equations. So when you put these first order systems in series, the resulting system is going to have second order dynamics. So the first two equations here, equation 1 and 2, represent the mass balance equations for tank 1. Equations 3 and 4 represent mass balance equations for tank 2. Now in total, there are at least 4 variables here: H1 Qi, Q1 H2, and Q2. I think in total there are 5 variables. What we would like to do is eliminate as many variables as possible and derive a differential equation only in terms of H2 and Qi. The algebra necessary to do this is very straightforward. differentiate equation 3 with respect to time, you get a second order differential equation. And then using 1 and 3, you can simplify that equation, eventually resulting in a second order differential equation of the form shown here. So here is the second order differential equation. Now this differential equation looks very similar to the standard second order differential equation shown earlier. The h2 in the differential equation is the y in the standard differential equation. The coefficient of the second derivative is tau square. Coefficient of the first derivative is 2 zeta tau. And the coefficient of the input qi is k. Similarly, there are other examples such as reactors where the dynamics could potentially be defined by a second order differential equation. Second order differential equations are also very commonly encountered when you have a closed loop system, where a process is in series with a controller. Together, even if the process and the controller are first order, together when they're in series, they are going to be second or higher order systems. Let's try to derive a transfer function for this second order differential equation. We subtract the steady state equation from the generic ODE, resulting in a second order differential equation in deviation variables. So once we take the Laplace transform and rearrange the terms, collect all the terms involving y and u separately, we can write down a transfer function for a second order system. And this transfer function is of the form k over tau square s square plus 2 zeta tau s plus 1. Always remember that on the left hand side we must have the Laplace transform of output in the numerator and Laplace transform of input in the denominator. Now here k is the gain of the second order process, tau is the time constant of the second order process, and zeta, which is not present in a first order transfer function, determines the amount of oscillations. When zeta is small, it is going to lead to large oscillations and vice versa. And this zeta is what is called a damping coefficient. It's important to note that there is no zeta in the first order transfer function, and therefore first order responses never result in oscillatory output unless the input itself is oscillatory. Now there are three important classes of second order transfer functions, and they are classified based on the value of the damping coefficient. If zeta is greater than 1, the process is said to be overdamped, and it will have roots of denominator polynomial that are real and unequal. If zeta is equal to 1, the process is said to be critically damped, and the roots of the denominator polynomial are going to be real and equal. If zeta is less than 1, the process is said to be underdamped, and the roots are going to be complex conjugates. In other words, if x plus jy is a root, then x minus jy must also be a root of the denominator polynomial. You never have complex roots appearing all by themselves. They always occur in pairs, in conjugates. The reason I'm trying to relate the roots of the polynomial to the response or the characterization of the response is because in the next lecture we are going to try and relate the roots of any given transfer function, the roots of the denominator polynomial of any given transfer function to its qualitative behavior. Now let's try to find the step response of a second order transfer function for a step input of magnitude m. We take the second order transfer function, multiply it with the Laplace transform of a step input of magnitude m. If zeta is greater than 1, the step response is given by the following time domain expression, where tau 1 and tau 2 are two roots of the denominator polynomial. As you increase the value of zeta, the response of an overdamped system gets faster and faster until zeta reaches 1.